All right, so number 2, we should have the supplement to be, or sorry, the complement to be 17.5. The supplement to be 107.5. Number 5, 2 complementary angles are congruent. Find their measures. That should be 45 and 45. Okay, so we could say x plus x equals 90, right? Because we know they're the same. Number 8. So it says name 2 complementary angles in this case. So you could say AFE, EFD, or AFE and BFC, right? Because you had a vertical angles and then that angle that was right next to it. Number 11, 2 acute vertical angles would be angle BFC and angle EFD. Number 14 we had in our notes, 155. 17 is 60. Number 20, you got to set those equal to each other. So 3x plus 8 is 6x minus 22. You get x equals 10. 23, the proof. Vertical angles are congruent. That's given. That vertical angles are congruent. And you're saying angle 1 is congruent to angle 4. And that's by transitive property used twice. Right? 26, it says they're complementary. Find the values of y, c, and d. So c and d, you're going to say 3y plus 5 plus 2y is equal to, what would it be equal to?
90.
90, very good. So then you solve y is 17, plug that back in. C is 56 degrees, and measure of angle D is 34 degrees. 29, find the measure of an angle that is half as large as its complement. X equals 1/2 90 minus x, and so that's going to be 30. Okay. Let's take a look at 32. So 32, oops, 32, no, okay. Okay, so 32. What do we know about this diagram? Well, we have vertical angles, right? So we do know these are congruent. But if I set up that equation, right, that's going to be in terms of x and y, right? So what's another equation that I could set up from this? It's another equation I could set up from this. What do we know about any 2 angles that lie on or any amount of angles that lie on a straight angle? What do you call it?
They're going to equal 180.
Yeah, they're going to equal 180. So we could say x plus 3x minus 8 is going to be equal to 180, right? So that'll give us 4x equal to 188. And so then x is going to be 47. Thank you. And then we're going to take that x, and we could plug it into the vertical angles and set them equal to each other. You could also say 47 plus 2y minus 17 is equal to 180. That would work too, right? And so then we're going to solve that. We're going to end up getting that y is 75. So I think a lot of guys overlook the fact that we have these linear pairs, right, that we know are going to add up to 180. Okay. Right? Other questions on that? Any others on the homework? You okay with that before we move? This was also the last problem in our notes from the vertical angle theorem. So if you want to fill those into your notes at some point, you could do that. You might already have that on your homework page, but that's exactly how we do that problem, okay? All right, let's go to 2.5, which is dealing with perpendicular lines. 2.5, perpendicular lines. So the first thing we're going to do is just define perpendicular lines here. So definition of perpendicular lines: 2 lines that intersect to form right or 90-degree angles. We use the same word for rays or segments that are perpendicular, right? So you can have perpendicular rays, perpendicular segments, perpendicular lines. That's fine. While we're here, why don't we write the converse of the definition? So if 2 lines are perpendicular, two lines are perpendicular, I'm just going to put perp, then they intersect to form right angles. I would say that's the conditional for the definition, right? So the converse of that would be, someone would say it? What's the converse of that?
If they intersect to form right angles, then two lines are perpendicular.
Pretty close. If two lines intersect to form right angles, so if two lines, that's just going to stay up front here, intersect to form right angles, then they are perpendicular. So the one reason why I want to say this is because, look, we have the definition, and when this portion of it comes up as a reason, or as a statement, I should say, then we could suspect if we get this as the outcome, then that's the reason, right? It's the definition of perpendicular lines. And then for the same thing, if we get this as a statement, right? They intersect to form right angles, and then we conclude they're perpendicular. Oh, the reason there would be definition of perpendicular lines, right? So I think that's why it was useful to write those out, okay? All right, symbol for perpendicular lines is this guy. It's an upside down T right here. Everybody see this? So that upside down T, that means perpendicular, okay? I often use that in shorthand or perp, okay? That's fine too. All right, so we got three theorems here about perpendicular lines. We can make a drawing to better understand these. If two lines are perpendicular, so I'm going to draw that right here. Two lines that are perpendicular, like so. We agree that if they're perpendicular, we got a right angle right there. Then they form congruent adjacent angles. So perpendicular right there, and then that just means that all of these are congruent adjacent angles. We should also know that they're all equal, right? They're all 90 degrees, aren't they? Next one, if two lines form congruent adjacent angles. So we're given this. Right, we have two angles and they form congruent adjacent angles. We can conclude what about them? They must be perpendicular. So notice that's the first diagram here, congruent angles, the second one showing that they're right angles. So basically what we're saying, if we have a linear pair and they're congruent, then we know that they're both 90 degrees. That's pretty easy to show too, isn't it? If you think about it, if we just call this angle 1 and 2, so we'll call this angle 1 and 2, we could say that 1 plus 2 is equal to what? What's 1 and 2 add up to? What do you think, Luke?
180.
180, right? Because it's a linear pair. Well, what do we know about 1 and 2? They are, what do you think, Matt? They must be, what do those symbols mean? They're more curved, so we're talking congruency here, right? Those two angles are given to be congruent, right? So if they're congruent, we could say 1 plus 1 is 180, right? And then that would give us 2 times the measure of angle, 2 times the measure of angle 1. Equal to 180, right? So then measure of angle 1 would be 90. So we just proved that 1 is 90, then we can substitute in, and 2 would be 90, right? They're perpendicular. So that proof would be pretty straightforward, I would guess, right? Angle addition, postulate, substitution, division, you're on your way, right? All right, the last theorem that we're dealing with here, if the exterior sides of two adjacent acute angles. So the exterior sides, right there, of two adjacent acute angles, if those, okay, we're going to call that angle 1 and 2, if those are perpendicular to each other. So we say that this ray, or yeah, this ray here and this ray right here are perpendicular to each other, then 1 and 2 must be complementary. 1 and 2, so if that's the case, measure of angle 1 plus the measure of angle 2 must be equal to 90. Okay. And that should be a pretty obvious result, right? Because if that's perpendicular, we know that it's a 90-degree angle. Furthermore, we know that angle addition postulate tells us that 1 plus 2 is equal to 90, right? So pretty easy output and theorem here. Okay. So when you want to reference these theorems, you can shorten them a little bit. Okay, let me just show you how to do that for one of them. So if two lines are perpendicular, just go like this. So for this one, two lines are perpendicular. I'm fine with that. Perpendicular lines. You can even drop the comma. Form congruent adjacent angles. So we can shorten the theorem to a phrase, right? And you got to come up with something that makes sense to both you and the reader, which is me in this case. We're not going to refer to this like in the book. This may be theorem, let me find it. In the book it says theorem 2-4. We're not going to refer to it that way because that's just particular to this book, right? So it could be a theorem in another book, it might not be at all, right? So let's just make sure that we shorten the theorems that we have here to something that makes sense, right? Obviously, this exterior sides of two adjacent acute angles one is a little harder to shorten, okay? Any questions on the definition and the theorems? Any questions there? Okay. All right, let's keep rolling here. So the next section is going to ask us to name or state the definition from this thing. We're going to use this diagram here that they provide for us. So first one, A, it says if A is angle 5, is a right angle, then RS is perpendicular to TV. So it's saying here's a right angle. We're going to conclude then that these lines are perpendicular. So did we see a definition or a theorem that basically gave us the exact same information? Did we see a definition, a theorem that gave us the exact same information? What do you think, Alan?
Is it the definition of perpendicular line?
It is the definition, right? Because that's just our converse of the definition that we wrote, right? So the definition of perpendicular lines. There you go. You don't even need to say the converse, just say definition. All right, does that make sense to everybody? We okay on that? So they gave us that it's a right angle and concluded that they must then be perpendicular. We noticed that's the exact same information that was in the definition, so we must be referring to that, right? All right, what about letter B? What about letter B? What do you think, John? So the lines are perpendicular, then 5 must be a right angle.
Is that the first theorem we went over?
Read it again. Lines are perpendicular, then the angles formed are right angles. Don't forget the very top thing, which is the definition. What does that say?
If two lines intersect to form 90-degree angles and they're perpendicular.
As the converse, right above that, read the actual thing that says definition.
Two lines that intersect to form right or definition of perpendicular lines is two lines that intersect to form right or 90-degree angles.
So the two lines intersect to form right angles?
Yes.
So what were we referring to here?
The definition of perpendicular.
There you go. Good. Definition of perpendicular lines. All right, let's keep moving here. RS is perpendicular to TV, so we have perpendicular lines. 8 and 5, these adjacent angles are congruent. These adjacent angles are congruent. Yeah, what do you think?
It's the first theorem.
Which would say
Perpendicular lines form congruent adjacent angles.
perpendicular lines form congruent adjacent angles. Very good. Yes, that is a theorem, right? That is a theorem. All right? Oh, getting tricky here. Don't get lost in the shuffle here on number or letter D. Angle 5 is congruent to angle SOV. Make sure you look at that. What's going to tell us that that's true? I'll give you a hint. It's not on your note template today. Not something that we've talked about today. What do you think, you?
Vertical angle theorem.
Vertical angle theorem, VAT. Vertical angles are congruent. Yeah? That's the theorem we had yesterday. Well, last time we read. All right, so it's perpendicular to TV. What is then going to tell us that the measure of angle 8 must be 90? Quickly, that must be?
Definition.
Got to be definition again, right? Because it's saying the lines are perpendicular, they must be 90. Definition of perpendicular lines. Angle 5 is congruent to angle 8, then they must be perpendicular. Luke, what do you think that would be?
Definition of
Does the definition say that the angles are congruent, then the lines are perpendicular? What type of angles are 5 and 8?
right angles.
No, we don't know that. We only know that they're equal and they're adjacent.
So does that mean there's like supplementary angles?
Now we do know that they're supplementary because they lie on the same line. But look at the theorems. You have 4 options here: definition and 3 theorems. So which theorem does it fit?
Is it
We have 2 congruent adjacent angles. What can we conclude?
if two lines form congruent adjacent angles and they are perpendicular?
Bingo. 2 lines form congruent adjacent angles, then they are perpendicular. Okay. Last one, OR is perpendicular to OV, then ROW and WOV are complementary. That's our last theorem, right? The exterior sides of 2 adjacent acute angles are perpendicular, then they must be complementary, okay? I'm not going to write that one out. You guys can do that on your own. Let's go to the sometimes, always, never. So perpendicular lines sometimes, always, never lie in the same plane. It's saying that there could be more than 2 lines being perpendicular to each other. And that's a hint right there in itself. So notice that it doesn't say how many lines you have. Another hint is, could we have, okay, here are 2 perpendicular lines like so. Could we have another line that would come in perpendicular to those? What do you think, John?
Yes.
How?
I guess kind of like coming this way.
Yeah, if you put an arrow through or a line through the board or your screen coming this direction, so coming from wherever, perpendicular to either of those 2 lines, we have 3, right? So this is going to be sometimes line in the same plane. Obviously, if it's just 2, they always lie in the same line, right? If it's 2 perpendicular lines, then it would be always. 2 lines are perpendicular if and only if they form congruent adjacent angles. Sometimes, always, never. What do we think? Matt? So 2 lines are perpendicular if and only if they sometimes, always, never form congruent adjacent angles. Is that one of our theorems?
Always.
Always, yeah, that's why. Because it is one of our theorems, right? If the exterior sides of two adjacent angles are perpendicular, then their angles are sometimes, always, never supplementary. Be careful.
Sometimes.
Sometimes,
Never.
right? The exterior sides are perpendicular, and the angles are really, that should say
Complementary.
complementary. So this has got to be never. Right? If they add up to 90, they can't also add to 180. Yeah. Vertical angles share a vertex. What do we think? That should be bingo. Quick.
Always.
Always, right? Just think of two intersecting lines, right? And so that's a vertical angle, that's a vertical angle. They have the same vertex. That's a vertical angle, that's a vertical angle. They also have a common vertex. Vertical angles are sometimes, always, never supplementary. Could they be equal to 90?
Never.
Careful. Could they be equal to 90?
Sometimes.
Could they be equal to 90? Yes or no? What do we think?
No.
Well, yeah, they could, right?
Oh.
That's possible, yeah. If they were perpendicular to each other. Is it always that way? No. So then we gotta sometimes. You gotta start running through these permutations in our heads, right? Vertical angles are sometimes, always, never complementary. Yeah, what would they have to equal if they were going to be equal and also complementary?
45.
45. Could that be the case? Could they
Yeah.
both be 45?
Yeah.
Sure. Yeah. Do they have to be 45? No. Got to be sometimes there. Pair of vertical angles are supplementary. Well, they better be 90 then. The lines forming the angles are sometimes, always, never perpendicular.
Always.
Always. That's just like the diagram I have right here, right? Everybody see this? Vertical angles are 90. These lines have to be perpendicular then, right? Okay. Questions on the sometimes, always, never? Everybody with us on that? All right, let's go to the next section. So this is just a little bit of application, okay? So BE is perpendicular to BF. Make sure you mark these well. So this guy right here is perpendicular like so. That means that this is also a right angle, yeah? And then it also tells us that BD is perpendicular to BF, right? BD perpendicular to BF, which would be this perpendicular like that. So we have all kinds of right angles going on in there, right? Okay. So the first 3A, it tells us that ABD is 2x minus 15. DBE is x. Well, we just said that ABE is a perpendicular, or is going to be a right angle, right? Based off of given information. So what do we know about ABD and DBE? Yeah, what do you think?
They're equivalent to 90.
Okay, so how can I set up an equation if we know that they're equivalent to 90 degrees?
X plus 2x minus 15 equals 90.
X plus 2x minus 15 would have to be equal to 90, right? The exterior sides of two acute adjacent angles are perpendicular, then they must be complementary, meaning they're going to sum to 90, yeah? So 3x is equal to, at 15, 105. And then we're going to get x is going to be equal to 35. Very good. All right. What about the next one? DBE and EBF. How do DBE, this guy right here, and this guy right here, how do those relate? What do you think, John?
They're equal to 90 degrees.
They're also equal to 90. So what are we going to do to them?
3x plus 4x minus 1 equals 90.
Very good. And so then that's 7x equals 91. And so then that tells us that x is
13.
13. Anybody else agree with that? Letter C is a little tricky here. Letter C is a little tricky. So, ABD, EBF. Take a look at that. ABD, so we're talking about this angle right here, and then the 1 and 2 dot angles. So big 1 dot, little 1 dot, and then the 2 dots. Right, those are the 3 angles we're talking. Well, a little bit of a hint there. We're actually talking about big 1 dot and 2 dots, yeah? So what do we think the relationship between ABD and EBF actually is? What do we think the relationship between ABD and EBF might be?
They're vertical.
They're not vertical, right? They're not sharing opposite sides as their, or opposite rays as their sides, right?
They adjacent.
Not adjacent either, because they would have to have a common shared side, right? No common interior points, common vertex. So no common shared side. Yeah.
That's something to do with how it shares DVE.
Yeah. Don't they share DVE to add up to what?
90.
Yeah. We see this. If we go 1 dot, this little 1 dot, and then this dot right here, these 2 dots, those add up to 90. Yeah. And then the big 1 dot and the little 1 dot also add up to 90. So we could say 3x plus DVE, right, equals 90, right? But we also know that DVE plus EF, which in this case is 2x plus 8, is also equal to 90. So we can set those two equal to each other, right? And what might we be able to get rid of by subtraction? Clearly, DVE. So we just kind of proved to ourselves, oh, this should say 2x minus 12, sorry dudes. We just proved to ourselves that ABD and EBF are equal. Do we see that? They're equal? We'll hear this the next time we do a lesson, but the complements of congruent or the same angle are congruent. The complements of the same angle are congruent. So anyway, we can say 3x minus 12 equal to 2x plus 8. So then that tells us that x is 20. Okay. Any questions on that? So I think the big thing here is just to realize that 3x minus 12 plus DVE was 90, but also realize that 2x plus 8 plus DVE was also 90. So we could substitute those, right, set them equal to each other, and then subtract out DVE quickly and solve for x. All right, the last one, ABD is 6x and FBC is 4x. So that's the outer parts here. This guy right here and this guy right here. So big 1 dot and big 2 dot. Well, what do we know about the angle that's in between those?
Right.
It's a right angle, so it must be.
90 degrees.
So we could say 6x plus, what's the big angle in the middle? 90
90.
plus
4x.
4x. It's on a straight angle, so it's got to be equal to 180. Bueno. So now we got 10x equals 90, yep. And x equals 9. So they're kind of throwing a little bit of everything in there for us, but yeah, not too bad, I don't think. So yeah, we have a situation where they're complementary, right? That was the first one. Another one where they're complementary on the second one. The third one, talking about complements of the same angle being congruent to each other, right? And the last one, all of them have to add up to 180 because they land on a straight angle. Yeah.
I don't totally get like the big dot and little dot thing.
I just refer to those as like ways to name angles without putting a number in there.
Oh,
Yeah, so I just say 1 dot, and then I already had 1 dot and 2 dots, so I just said the bigger dot and the bigger 2 dot. It'd probably be easier if I just numbered them 1, 2, 3, 4. Okay. So our homework on this is going to be a section from this particular section, and then actually and some review, and then you have another homework which would be actually technically from 2.6, but it's all just like name what tells you that, like what definition, postulate, or theorem, right? So it says it's a new section, but it's really just review. So those are our 2 homeworks.